Hello everybody. Welcome back to Math 245. This is lesson 13. Last time on Monday we talked about how to graph linear inequalities as well as how to graph linear systems of inequalities. Today we are going to be using those techniques in order to create a feasible region of a function, or functions actually will always have more than one, given a set of constraints. So constraints are conditions that must be satisfied when trying to optimize the objective function. Today we're not going to worry so much about this objective function or optimizing it. Optimizing here means minimizing or maximizing. We'll focus on that on Friday. And the set of all points satisfying these constraints is called the feasible region, which is what we are going to focus on today. And we have this theorem called the fundamental theorem of linear program, or the corner point theorem, and it says the following. The fundamental theorem of linear programming states that the maximum or minimum, this is the optimized value of the objective function, always takes place at the vertices or corners of the feasible region. So like I said, on Friday we are going to focus on the objective function and how to maximize or minimize that, but today we are only focusing on how to construct what we call this feasible region. So we'll look at this example on Friday. So given a bunch of constraints like we have here, how do we plot this region where this region contains all of the points that satisfy these constraints? Well, let's look at our first example. We want to graph the feasible region subject to the following constraints. Clearly mark the corners of the feasible region on the graph. The corners are important because of our theorem up here. So I'm going to graph each of these regions separately, and then I'm going to find where they all overlap, and that will be my feasible region. So let's look at the first one. X is greater than or equal to -2. So if I graph the line x is equal to -2, that line will be here. Let's see. X is greater than or equal to -2. Here is x equals -2. And I want to be greater than -2 or equal to. So my line is solid because I can equal that value. And then I have, whoops, this whole region right here satisfies this guy. X is greater than or equal to -2. Next, I want x is less than or equal to 8. So if I graph x is equal to 8, that guy is right here. And here I have a solid line again, since I can equal the value 8. And now I want to be less than 8. So that is over here. So far I see that my possible region is contained between these two vertical lines. So that's this one. Next I have y is less than or equal to x. So I'm going to draw the line y equals x, which is this. It's solid since I can equal that value. And I want less than or equal to x. So I need to plug in a point. I can't use 0, 0 here. That's my favorite point to use. I can't use it here because it's on the line, so that wouldn't really help me out. So I am going to test a point. Let's do 1, -2. 0.1, -2, which is here on the graph. So I want to see if that point is in my shaded region for this particular function. So I get y is less than or equal to x, this gives me negative 2 is less than or equal to 1, which is true. So this point is included in my shaded region. So I need to shade in that region. That means it's this whole thing right here. Okay. Finally, I have y is greater than or equal to 0. So far, just to recap, my feasible region is in between my two vertical lines where I have the red portion as well. So far, my feasible region is right here. And now I have one more constraint. Y is greater than or equal to 0. So I need to graph the line. Y is greater than or equal to 0. And it's going to be solid. Here is the line y equals 0. And I need to be greater than it. So I am all up here. So this tells me that, oops, oh gosh, nope, oh gosh, I just erased everything. That was terrible. Oh, here we go. There we go. So this tells me that my feasible region here is where my four colors intersect. It's kind of hard to see, but I'm between these two vertical lines with the red portion and the yellow portion. So that means that my feasible region is right here. Let me make it a little bit darker. This is my feasible region. So that means that all of the points in this little area satisfy every single one of these constraints. So all of the x values are between negative 2 and 8, y is less than or equal to x, and y is greater than or equal to 0. So we simply drew each one of these constraints individually. We shaded in their regions where the inequality was true, and then I found where all of these regions intersected with each other. Let's do another example. I want to graph the feasible regions subject to the following constraints. Clearly mark the corners of the feasible region on the graph. So my first equation is x plus 2y is less than or equal to 6. Well, I need this into y equals mx plus b form so that I know how to graph it. So I have x plus 2y less than or equal to 6. If I subtract x from both sides, I get 2y is less than or equal to negative x plus 6. And finally, dividing by 2 gives me y is less than or equal to negative 1/2 x plus 3. So if I were to draw this, I have a y-intercept of 3 and a slope of negative 1/2. So here is what my graph looks like of this function. It's solid since I can equal this line. And now I just need to test my region. Which one is it going to be? So I need to test the point 0, 0. So I have y is less than or equal to negative 1/2 x plus 3. If I plug in 0, 0, I get 0 less than or equal to 3, which is true. So the point 0, 0 is included in my region. So let's graph this. So this is my region that I care about. That's the first one. My second equation is 3x plus y less than or equal to 12. Well, again, I want to get it into y equals mx plus b form, so I first need to do that. So I have 3x plus y. That's confusing, isn't it? 3x plus y less than or equal to 12. So I subtract 3x over to get y is less than or equal to negative 3x plus 12. So my y-intercept is 12, which is way up here off the graph actually. And my slope is negative 3. So I am going down 3 over 1, down 3 over 1, down 3 over 1, all the way down. So this is the other line. I need to see which region, to the left or to the right, basically, I need to shade. So I'm going to plug in 0, 0. You can plug in any point. It's just that 0, 0 is really easy. So I get y is less than or equal to negative 3x plus 12. And if I plug in 0, 0, I get 0 is less than or equal to 12, which is true. So I need to shade in the side that has the point 0, 0. And that gives me this region right here. Of course, we want to focus on the intersection of the two regions, which we can see pretty clearly. And then I have one more constraint. X and y is greater than or equal to 0. So I need to graph the lines x is greater than or equal to 0 and y is greater than or equal to 0. So first of all, this one is blue, this one is red. So let's first focus on x is greater than or equal to 0. So when I graph this, x is greater than or equal to 0, well, that is going to be a vertical line, and I'm going to be greater than or equal to 0, so I'm going to be all over here. And our last one is y is greater than or equal to 0. Well, that is this line right here, and I am above 0. So I want the intersection of all of these regions. And if we look closely, I see that the region of intersection is this little piece right here. It's a little tiny piece, but that is the region of intersection between all of these functions. So in this is what we call our feasible region. This satisfies all of these constraints. This is where x and y are greater than or equal to 0, and is where my two other inequalities are true. So pretty cool, huh? All right. Well, that's it for today. We'll be working more with this kind of stuff on Friday, focusing more on our objective function and optimizing our objective function. And so I will see you on Friday. Have a wonderful day.